The final piece to our basic derivatives unit includes finding the derivatives of all 6 trig functions. You got your sine, cosine, tangent, cotangent, secant, and cosecant. So our objective here to derive and use the derivative rules for the trig functions. Speaking of trig functions, if you take a look at this image here for our objective, you've got a movie poster for the screen adaptation of Edgar Allan Poe's The Pit and the Pendulum. And if you don't know anything about this, like the pendulum swings backwards and forwards and it lowers at the same time, little by little, and then, of course, cuts this guy in half. This guy's not having a good time. You can see it by the look in his eyes. Anyway, I chose that image because a pendulum, as it swings backwards and forwards, is an example of simple harmonic motion, which can be modeled by sines and cosines. Okay, so we're going to start off with an investigation very similar to how we did the exponential function. To find the derivative rule for f of x equals sine x, approximate its derivative graphically using the difference quotient with an infinitesimal value of h. Okay, so here we have the limit definition of the derivative, and then, of course, we want to just approximate this by choosing an h value that's really, really small, infinitesimal, like 0.001. So I'm going to put this in my calculator thusly, just like I did for the previous one, the one for e to the x. So in one of my equations, say y1, I will put sine x, and then y2, I will put in the difference quotient using a very small h value right here. Okay, so I'm going to do this investigation on Dismos, as I do, sponsored by. Okay, so we'll start off with an f of x, I think, and then equaling sine x. Right, and I think it defaults to radian mode, which is fortunate because that's all there is in calculus. Okay, so here is the graph. I don't like the color of this being red because that's the official derivative color, something like that. Anyway, so I'm going to change this color to something like purple. Okay, and then let's come down here to number 2, and let's fake a derivative by taking g of x being equal to, let's put parentheses around the whole numerator. It's going to be f of x plus h, and our h value is going to be real small, like 0.001, arrow out of that, minus f of x. And then all of this supposed to be divided by that same h value, 0.001. Now, of course, whenever you're doing this, if you're doing it on your own graphing calculator, you're going to use like y1 and y2 on yours. All right, and again, I don't care for the colors on this one. Maybe green. Okay, and then also maybe dotted. There we go. This looks fantastic. All right, so the original purple graph there's sine, and this is a super close approximation to the derivative of sine. Well, that looks awfully familiar. Let's see, it hits at 1, at 0, and this number that's, what the heck number is that, 1.57? I think this is like pi over 2. It hits right there at 0. What graph is that green one? It looks like cosine. And this is kind of astonishing that the derivative of sine is its cofunction, it's cosine. So what does that mean? That means that if I wanted to find the slope of any point on this purple graph, sine x, all I have to do is plug that x value into cosine, and it tells me what the slope is at that particular point. Here, let's summarize that right here for the sine and cosine rules. So the derivative with respect to x of sine x is just cosine x. So in purple, you've got the sine x graph, and then in green here, wow, this is like the exact same colors that I chose on Desmos. It's like I've done this before. And again, like if I wanted to find the slope at any particular x value, all I have to do is look at the graph of cosine x. So for example, this was day 1 activity in calculus. Remember, you were fooled by thinking that the line y equals x with a slope of 1 was, well, actually it was sine, but I Fooled you into thinking it was y equals x. But hey, the slope there is 1, and so is cosine. Let's come right over here to pi over 2. If you zoom in right there at pi over 2, it's going to get more and more horizontal. It's a peak. It's a relative maximum. Slope is 0. So right there on cosine, it's also 0. Right there, right? Okay, maybe another point. How about right there at pi? Looks like it's at -1. Cosine of pi is -1. And if I look at, let's say 3 pi over 2, cosine of 3 pi over 2 is 0, and so on. Okay, so let's look at, let me go back over here to Desmos, and I'm just going to change my function. Let's change this sine function to cosine. It's probably going to freak out after I delete out everything for sine. Okay, let's put cosine in here. Okay, so now cosine is the purple graph, and then the green graph is its approximate derivative. So it almost looks like sine, but it looks like it's flipped over, because sine, remember, it has a +1 slope right there at the origin. This one is a -1 slope here. It's the negative of sine for the derivative of cosine. So here, let's summarize that as well. So the derivative with respect to x of cosine x is negative sine x. Now notice that the derivative of the cofunction is negative. This is going to be a very common thing that happens with the derivatives of cofunctions, as you'll see. Okay, so here in green, I have my cosine function, its derivative. In purple here is negative sine. So once again, if I wanted to find the slope at any particular point right here, all I have to do is plug it into negative sine. So at 0, sine of 0 is 0, -0. And then there's my slope. Or here, let's pick another one, pi over 2. So the sine of pi over 2 is right there. It's at 1, but we're taking the negative of it, so it's -1, and so on. All right, in the next video, what we're going to do is we're going to attempt to actually prove this. We used just graphical evidence to suggest that each of these derivative rules are what they are, but now we're actually going to use limit definition to actually prove them.